Okay, welcome back. It's a pretty short lecture today, so I'm sure you're all very excited about that. I want to make a comment right here. The book says, adding up fields over curved surfaces volume is commonplace. We've already done this for scalar fields. We have not. I don't know what your book is talking about. This is section 11.7, as in next week. So don't pay too much attention to those first couple lines and expect that we actually have done that before. But with that said, I will comment really quick on what it's trying to talk about. If you're given a scalar field, this is maybe foreshadowing or something, I don't know what you want to call it. If we're given a scalar field, this scalar field changes in three directions, right? So it changes in x, y, or z direction. Very standard. This is why we have the gradient, all those classic great ideas you've already developed so far. Well, what that means is that every time it changes in a direction, we can integrate in one of those directions. Okay, and that's what this dx means. I mean, traditionally, if we were truly integrating this, we would put an integral in front of the a to b or something like that. But that's what the dx means. You could integrate in two directions, and this is an area under the curve. This is a volume under the curve. This would be something more general than a volume under a curve, and so on. So each of these could potentially be integrated. We're going to get there in section 11.7. But the idea of today is that, okay, what if I care about an integral in a direction which is not x, y, or z, or perhaps a changing direction? Right. What if I want to integrate along a curve? That's maybe what I should say. I.e., can we integrate along curves? And I wouldn't be asking this question if the answer were no. So yeah, we can integrate along curves, and we're going to see how we do that today. In this sense, rather than integrating along curves for scalar fields, we're going to actually modify our way over to vector fields. So not scalar fields, where we would output a scalar, we're going to get vector fields and integrate along curves through vector fields. Okay, so let's talk about these. These are called line integrals. So the integration of a vector field along a curve is called a line integral. And let's see how we define those. So for a given vector field f and a given curve gamma, from the minimum time, wherever the curve starts, we're going to call A, and wherever the curve ends, we're going to call B. The integral along that curve from A to B is defined by, see, it's the integral, the quote-unquote bounds of the integral, r gamma, the curve itself. It's the vector field dot product, the differential of the curve. And what is the differential of the curve? It's not that hard for us to calculate. What should this be? D gamma of t. We know our chain rule from the last chapter should be gamma dot of t dt. So that really shouldn't be much of a surprise, and that's where we see gamma dot t dt show up. And of course, f is integrated along the curve, meaning that the input of f is the curve itself. Okay, so how should we think of this? We're computing how much the vector field aligns with the tangent vector of the curve. Right, so if I have some vector field here. Let's do something nice and fun, vector field wise. So suppose this is my beautiful vector field f. And I take some curve that I'm going to draw through here. In red, this is gamma. What I'm thinking about is how often was gamma aligning with the vector field. So for example, right here, maybe I'll go right there. Right there, gamma and the vector field don't align at all, right? They're kind of pointing perpendicular to each other. Meanwhile, over here, they align pretty well, and over here, they align very well. And so we're going to gain more integration parts where they align and less integration parts where they do not align. The reasons why some of these might become important is, for example, magnetic fields. If we take the motion of an electrically charged particle through a magnetic field or an electric field, then we can calculate quite a few quantities using line integrals. So you can think about the curve as the motion of a particle and the vector field F being either electric or magnetic fields. And we're going to calculate quantities of that. Okay, these are not that hard to calculate because at the end of the day, this is a simplify, and then it's a integral from Calc 1. Okay, so these are not really hard to calculate. You just have to remember the formula. But let's look at a nice example. So yeah, so here's a good example, I suppose. The total work done on a particle as it moves through a force field is calculated with line integrals. So let's consider my force field F of xy as 2x and 3y. Meanwhile, the path that a particle takes through that force field is t squared, and the time interval is 0 to 1. So before I even look into all of, at the solutions, let's just think to ourselves, how should we set this up? Because it's not that hard to set it up. So the first thing I need, say steps for line integral. The first thing I need is gamma prime, or gamma dot. The second thing I need is to just set it up as t0 to t1 f of gamma dot dt. And then the third is to calculate. So if I'm using those, step 1, I need to calculate gamma dot. I know it's already on the screen, but let's pretend it's not. Calculating gamma dot, I take a derivative of t, I get 1. I take a derivative of t squared, I get 2t. I then set up my integral in step 2. It's the integral from t0, which is 0, to t1, which is 1, of f of gamma. And this is one reason why we care about compositions, right? F of gamma. So if I plug gamma into f, that means every time I see an x, I'm plugging t in. Every time I see a y, I'm plugging t squared in. So I see an x, I plug t in. I see a y, I plug t squared in. I take the dot with gamma prime, or gamma dot, 1, 2t, and this occurs dt. From this point onwards, all I have to do is calculate. Right, so this shouldn't be too tricky. I'm actually going to compute my dots. So the dot product here is going to be 2t plus 6t cubed dt. And we all know how to integrate 2t, that becomes t squared. 6t cubed becomes 3 halves t to the fourth. 0 to 1, I'll end up with 1 plus 3 halves, also known as 5 halves. Then there's the last thing I want to cover today. Remember I said it was a short chapter, is that this notion is very important in defining what's called the potential of a vector field. So it turns out we will be able to construct potentials of vector fields by using very cleverly constructed line integrals. So I'll show you how to do that in the next section. Anyway, that's all I have. See ya.